right, this is geometry, still on chapter 8, lesson 4. Now we're talking about some different types of transformation. We're going to give them new names. Well, we're going to tie the old names with a new name. We're going to actually put two concepts together. All right, so I made this equilateral triangle this morning. This is an equilateral triangle. It is. I cut it out this morning. So that every side is equal. Well, they're probably maybe decimal places off. I did the best I could. So this image looks the exact same as this image, doesn't it? And it looks the exact same as this image. What kind of transformation is this? What kind of transformation is this?
Rotation.
It's rotation. It's rotation. Where is the center of rotation? Well, we're going to learn that later. It's somewhere in this triangle. It's equidistant to every vertex. It's actually called the centroid. We'll learn that later. No, not this lesson. All right. So, probably here, somewhere here, is the center. All right. Now, normally when we think of rotation, we think of this, right? Right? Something like this, such that the center of rotation is outside the image. Oh my goodness, the image fell. Right? But when we have a rotation such that the center of rotation is inside the image, we can rotate it and it look exactly the same, right? On this center. That won't stay where it's supposed to stay. This is called rotation symmetry. Rotation symmetry. A figure has rotation symmetry if I can rotate it about some degrees less than 360, such that when I rotate it, it looks exactly the same. So, how many degrees am I rotating it to get here? Okay, so how many?
No, it's more than 120.
A 120. How did you get 120?
Because I divided 360 by 3 since it can turn 3 times.
Correct. I can rotate it 3 times and get back to the original. So that's 1, 2, 3 to get back to the original. So you take 360 degrees, which is all the way around, and divide it by how many times you can rotate it to get the degree through which I rotate it. Okay. All right. This card also has rotation symmetry. How many degrees do I need to rotate it? How many?
Wait, to rotate all the way around?
How many degrees do I have to rotate it so it looks the exact same?
180. Oh wait, 180. I'm sorry.
180, because I just rotate it twice. You get it? You get it? I rotate it twice and it looks the exact same. Does that make sense? It has to be, you have to be able to rotate it through less than 360 degrees for it to look the same. Now, thinking about that, are you with me? Okay, I want you to think about this. What figure has infinite rotation symmetry? What?
Circle.
A circle. That is correct.
Sorry, I wasn't.
Okay? Elliot, how many degrees do I have to rotate a square such that I see that exact image? How many degrees? 90. That is correct. Yes. Wish I'd done a square too. I'm gonna make a square. Okay, yeah, because it would be here. 1, 2, 3, 4, right? And I take 4 divided by 360 divided by 4. What if it looks like this? I can still do it. It's a square. The diagonals are going to be equal. So 1, 2, 3, 4. Okay, now I want you to think about this. What about a parallelogram? Does parallelogram have rotation symmetry? Yes.
No. Yes. If you were to rotate it 180 degrees.
Yeah, because B comes here, right? What goes here?
C.
C, which is further in. C goes here. What goes here? A goes
There.
there, maybe. And so D goes, it's further out,
Yep.
right? It has rotation symmetry. Through how many degrees? 180 degrees. Yes.
What about a shape where you can't even find like a center because it has all these weird jagged
Then
convex
it-
and concave?
So not every figure has rotation symmetry,
Okay.
right?
Yeah.
All my cards have rotation symmetry.
Don't rip your cards.
I'm not gonna rip my cards.
I like cards.
Ah. Okay. This card does not have rotation symmetry. Why?
He's a 6.
Okay.
Spade, not that.
Because of the spades, not because of the 6. What happens to the spades in the middle?
They point down.
They're upside down now. When I go this way, they're right side up. I originally looked at the diamond. The diamond does have rotation symmetry, right?
The heart. What about the heart? The heart doesn't.
I bet the heart doesn't either.
Neither does the club.
Neither does the clubs. That's correct. Only the diamonds. And I believe all the face cards do. Because of the way they're drawn. Okay, so we can know about rotation symmetry. It's how many times through what degrees I can rotate something such that it looks exactly the same as the original. Got it? That is rotation symmetry. Look at the plate with the horses. How many horses are on this plate? Everybody count. You got it? Yes. You can get what you need to get. Right here. Here, David.
Wait,
Can everybody count the horses?
where?
On the plate on the top of page 319. Let's see if you can get the right number of horses.
Oh my god.
I'm glad I wrote how many are in my book.
12.
5, 6.
Luke, what do you think?
I think there's 8. Wait, no.
12, right?
1.
Oh, there's 12.
Chris.
There's 12.
I was gonna say 18.
12 is correct.
Yes.
12.
There's 12, but there can only be 4 horses because there's only 4 heads. Right?
Do you think? Or maybe
Yeah.
one head is exactly behind it.
Yeah, Jack, why don't you call the cops slowly? Should you?
There's 12. And if you ignore the damages on the plate, you know, the chips, you can rotate it about 90 degrees and it looks the same. So that's rotation symmetry. Turn the page to page 320. Parallelograms have rotation symmetry. So there's this concept called fold symmetry. The N just says how many times can I rotate it such that it looks the same. So a parallelogram has two-fold symmetry. Got it? Two-fold symmetry. What about a square? What fold symmetry does a square have? How many times can I rotate it and look exactly the same? Four-fold symmetry. Are you getting it? My equilateral triangle. How many fold symmetry does my equilateral triangle have? Three-fold symmetry. All right, so there's two concepts that you can look at. Two new ideas. We look at how many times we can rotate it, and that's blank fold symmetry, right? We also look at the degrees through which we rotate it. An isosceles, what about an isosceles trapezoid? What type of symmetry? So what does really symmetry mean? It means the same as. It looks the exact same. That's what symmetry means. So my equilateral triangle has rotation symmetry. I can rotate it. What about an isosceles trapezoid? What is true about an isosceles trapezoid? What makes an isosceles?
The bases are
Both
The legs
bases
are,
are parallel.
Say it. Yes, the legs are equal. That makes it isosceles. What type of symmetry? Can I rotate it? Does it have rotation symmetry?
No.
It does not. But it has what's called reflection symmetry. So there's rotation symmetry. What is rotation symmetry?
When you rotate the shape, then it looks the same.
Yes. With rotation symmetry, we have like in fold, that's how many times, that's the number of times I can rotate it so that it looks exactly the same. And then we have degrees. Okay, I'm gonna put theta. And that's the degrees through which we rotate it. Okay, so those are the two concepts with, yes.
And yours.
Just 1 minute. Can you wait a minute? All right. So this isosceles trapezoid has reflection symmetry. So see how we've tied this symmetry word to the transformations? You see that? We're just adding that word. Okay, so what is reflection symmetry? Reflection symmetry happens if there's a line through which I can draw on that figure. Do you see how these symmetries happen within the figure, whereas the transformations sort of happen outside the figure when they're alone? Do you see that? Okay, so a reflection, if I'm not talking about symmetry, a reflection would be like here to here. Reflection symmetry would be like here. This side is the exact as this side. Does that make sense? Do you see the difference? All right. So you have this line of symmetry through which you can draw through the image such that you could fold it and every vertex, every distance would match. Does that make sense? That is reflection, sometimes called line symmetry. Okay, what other shapes have line symmetry? Isosceles trapezoid. What else? What? Triangle. Every triangle? No. Which kind of triangle?
The
Equilateral.
and the isosceles. I think.
And the isosceles. Isosceles would. Okay. How many lines of reflection can I draw through this? 3. That is correct. if it's equilateral. Only if it's equilateral. If it's isosceles, it would just be 1. But let's assume that this is an equilateral, okay? This would be a line of symmetry. This would be a line of symmetry. This would be a line of symmetry. Got it? What about a square? How many, is a square, does it have reflection symmetry?
Yes.
How many? Okay, where would the 2 go? Do you think there's more?
I was thinking of rectangles.
Four.
So you can.
4.
No, it's corner to corner. It's
Yeah.
actually small.
Corner to corner,
So,
and here to there. 4. 1, 2, 3, 4. Looks like a bunch of lines, doesn't it? But it's 4. Okay, so reflection symmetry is you can draw a line through the image such that one side is an exact reflection of the other side. Make sense? Do parallelograms have reflection symmetry? They do not. Parallelograms have rotation symmetry, not reflection symmetry. Trapezoids have, isosceles trapezoids have reflection symmetry, but not rotation symmetry. Got it? Now look at the last one on the bottom of page 320. Translation symmetry. A pattern has translation symmetry if it coincides with the translation image. So the red one in that picture is the original image. And what have they done? They've just moved it. They've translated it, right? Through lines that are parallel. That is translation symmetry. All of these are isometric, right? They're all isometries. All of these symmetries are isometries.